Hello. Can everybody hear me? Okay. I guess the people who can't wouldn't respond anyway. But anyway, we'll get started on this week's tutorial. So, first question. We're going to compute the cylindrical velocity and also the cylindrical acceleration vectors of an ant moving on a cylindrical path. So I guess if you imagine a log, maybe the ant is walking around it. So it can't go off the log and it can't go into the log. So it's just walking around the log. So we've got the path of the ant is given by x is cos phi, y is sin phi, and z is given by z, where as a function of t, where z is sine t squared. And so just by inspection, we can see that. Sorry, I've lost my mouse. There it is. So, in cylindrical coordinates, you'd have x is equal to rho cos phi and y is equal to rho sin phi. So just by inspection, we've got it's a cylindrical path, and we can see that the radius rho would be given by just 1 in this case. It's just a constant, so the radius of the cylinder is not changing. And so we're in cylindrical coordinates. So to find the velocity vector, in cylindrical coordinates, that's given by so v of t, it's d rho dt in the direction of the radius, or rho, and then it's rho d phi dt in the direction of phi, and it's dz dt in the direction of z. So from above, we've got, so now we've got rho of t is equal to 1 here, phi of t is just t, and z of t is equal to sine t squared. So from this formula down here, we need to find, we need to differentiate all of those with respect to t. So d rho dt, so rho is just 1, so if we differentiate that with respect to t, we just get 0. D phi dt, so phi was equal to t, so if we differentiate t with respect to t, we just get 1. And if we differentiate z with respect to t, so z was sine t squared, so that would be equal to, so if we differentiate cosine, we get, sine, we get cosine, but then we also have to differentiate the bit inside, so we get that cos t squared by 2t. So now we can put that into the formula for the velocity vector. So the velocity vector is given by so d rho dt is equal to 0, so it's 0 in the phi direction, and then rho is equal to 1, and d phi dt is also equal to 1, so 1 times 1 is still 1, so we just get 1 in the phi direction. And then dz dt was this 2t cos t squared in the z direction. And so what I've noticed about that is that in this case, the velocity vector is everywhere. Is that big enough, or should I make it a bit bigger? But the velocity vector is everywhere tangential to the cylinder or the log. And we can see that that's the case because the component that's in the direction of the of rho is equal to 0. So now we can find the acceleration vector as well. And feel free to stop me if you have any questions. So it's similar to how we found the velocity vector. We have a formula for the acceleration vector in cylindrical coordinates. And so we have the second derivative of rho with respect to t minus rho d phi dt squared in the rho direction. And then in the phi direction, we've got phi, the second derivative of phi with respect to t, plus 2 d rho dt times d phi dt. Plus the second derivative of z with respect to t. And so, again, we just have to find the relevant derivatives and then substitute it into that formula. So the second derivative of rho, so the first derivative was 0, so it's still 0. The first derivative with respect to phi was 1, so now when we differentiate that, we get 0. And when we differentiate z twice with respect to t, so first we have to differentiate the 2t and leave the cos t squared alone. And then we have to differentiate, we'll leave the 2t alone and differentiate the cos t squared. So we'll get another 2t, so we'll get 4t squared, we'll go back to sine, and of course the negative. Okay, so now we just substitute that in our formula for the acceleration vector. And so, don't know if you recall, so the second derivative we get just 0 minus 1 by 1 squared and then we get 1, but we multiply that by 0, so it's just 0, and then we get 2 times 0 by 1. Don't know if I can get all of this on the screen at once. And then we just need to, so it's the second derivative of z. So that's 2 cos t squared minus 4t squared sine t squared. And so that's equal to minus 1 in the row direction plus nothing in the phi direction plus this function of t. In the z direction. So this time there is a component of the acceleration vector in the direction of the in the direction of rho. So that's pointing into the cylinder. So we've got a component that's normal to the cylinder and pointing inwards because it's minus 1 in the direction of rho. Did anyone have any questions about that first question? I'll move on then.
Sorry, can you just help me to review about the velocity? How to just calculate the velocity about the derivative?
So we're in cylindrical coordinates. So this is what the velocity vector is given by, and we into the necessary derivatives and just substitute that into the formula. Does that make sense?
Yep.
Cool. Okay, for question 2, I'm just going to look at just one function rather than 3, but I'm going to complete all first order partial derivatives of this function. So first we're going to look at, so we've got a function of x, y, z, and first I'm going to look for the partial derivative with respect to x. So df dx, so thinking about y and z as constants, if I differentiate this with respect to x, I just get 1 over the square root of y squared plus 3z. Can everyone see that that's the case? And then I'm going to do the same. I'm going to sort of treat x and z as constants, and I'm going to differentiate with respect to y. And so for this, I might find it useful to write it as xy squared plus 3z to the negative 1/2. So to differentiate with respect to y, bringing down the half, so nothing happens to the x. The x is just a constant, so it's minus x on 2 y squared plus 3z to the power of minus half minus 1, so minus 3 on 2. And we multiply that by, so it's the chain rule. We're differentiating now within what's in the brackets with respect to y, so we just get 2y. So the 2's cancel out, and we just get minus xy on y squared plus 3z to the 3 on 2. And now we're going to do the same for z, pretending that x and y are constants. And so similar to when we found df dy, I need to use the chain rule. So we get minus x on 2 y squared plus 3z to the minus 3 on 2. And this time we need to differentiate what's in the brackets with respect to z. So we get 3. So that's going to be equal to minus 3x all on 2 by y squared plus 3z to the 3 on 2. So that one's pretty simple. Was there any questions about that one? I'll move on then. So for this question, I have a contour diagram. And so we've got these contours. So this is the smallest contour down here. It's -5, and they're going up in steps of 2 all the way up to this contour is the highest. It's at 11. And so we've got the x-axis down here from 0.7 to 2.2, and the y-axis is here. So just by inspection, I can see that A is the point at 1, 1, and the value of the function described by the contours is at this point. If we look at the contour, the contour is 1. So the function is equal to 1 along this line, which A is on. And B, similarly, we've got that it's at 1, 1.5, and it's on the contour for the function value 5. And now C, it's not directly on a contour, so I've had to sort of go, oh, but it's halfway between the contours minus 3 and minus 5, so I estimate that that's about minus 4, and it's at the point 2, 1. So with A as the reference point here, we're going to compute the average change in the function from A to C. So you'll have a formula to find sort of that average change in the function, but because A and C have the same y value, there's no change in the y value. So the path length given by, I'll write it in a moment, from A to C simplifies to, so see if I can, perhaps I haven't left myself enough space. So the path length change in S simplifies to just the change in X. And so that's because, as I was saying, because there is no change in y. Y is equal to 1 for both A and C. So hence the average change in F from A to C is given by, try to do that here. So the average change in F from A to C is given by the change in F over the change in X. So it would have been, if it was changing in Y as well, that it would have been the change in S, the path length. And so at C, the function is minus 4. And then we take away what the function is at A, which is 1. And then, so the change in X, so X at C is 2. And we take away what X is at A, which is 1. So that's given by minus 5 on 1, or just minus 5. Did anyone have any questions about how I found that? So now, part 2, I'm going to do something similar, except this time, when I'm looking at the average change in the function from A to B, this time there's no change in x. So x is just constantly 1 along this. So the path length from A to B simplifies to just the change in y, because there's no change in x. Essentially, the change in x is 0. So, when you've got the change in s is equal to the square root of the change in x squared plus the change in y squared. So, if one of these is 0, then the change in s is just equal to the change in x or the change of y. So now we're looking from A to B. So that's given by change in f, change in y. So this time the function value at B is 5 minus the function value at A, it's still 1, and then it's change in y. So the y value at B is 1.5 and the y value at A is 1. So that's approximately equal to 4 on 0.5 or 8. So now, there were no questions about that. So part 3, so we want to use those results that we found. So the average change from A to C was -5, and the average change in the function from A to B was 8. So given that, we can sort of find an approximation of the gradient vector at A. So an approximation of the gradient vector at A would be given by so that change in f over change of x in the direction of x, and then the change in f over the change of y in the direction of y. And so we found this to be approximately equal to -5 using the points A and C. And we found this here to be approximately equal to 8. So that's an approximation of the gradient vector at A. But if I actually knew the function that described these contours as we are given in part 4, so the function is actually, so it's a function of x and y, and it's -x squared minus 2xy plus 4y squared. So given that, we can now actually find the exact value of the gradient at A. We don't have to use that approximate one we just found. So that's given by, the partial derivative with respect to x, I, plus the partial derivative with respect to y. And so if we differentiate that function with respect to x, we get minus 2x minus 2y, sorry. And there's no x in the last term, so that just goes to 0. And then when we differentiate with respect to y, there's no y in the first term, so that doesn't do anything. We get minus 2x plus 8y to the 1. And so at A, so that's the, I guess the that's the gradient vector, but we want to find the gradient vector at A. So we want to find this at 1, 1, because that was where A was up here. So minus 2 is minus 4. Eight is 6. So I think that's oh no, that's right. So if we think about that compared to our approximation, so our approximation, if you recall, it was minus 5i plus 8j. So what do you mean? Perhaps I've done it the delta f, the upside down triangle. Yes. So this is, I mean, I'm using the same notation that Michael Bridson has given me. So when you're looking for the change in the change in x and y, then you've got it up this way, but then grad f is use the nabla, or the upside down triangle. So anyway, if I compare it to my approximation, the approximation is much better in the x direction than it is in the y direction. Which is, I think, because the contours are more spread out and changing less in this direction compared to this direction. But I don't think you have to actually comment on that. But even if you do, you're looking at the answers. It's like in the x direction, when you're going towards C, where we're losing, like the function is decreasing, but then as you're going up towards b, the function is increasing. So it makes sense that I guess that this is negative and this is positive. Okay, so that's part 4. We'll go on to part 5. And so for this, we want to compute the magnitude and direction of the gradient at A, and describe its orientation with respect to A and the contour passing through it. So perhaps that's what I've just done a bit. So the magnitude of the gradient f at 1, 1 is just equal to the component for the, so we've got that vector minus, so grad f was minus 4i plus 6j, so it's equal to minus 4 squared plus 6 squared, so that's 16 plus 36, or root 52, or I've simplified it to 2 root 13. And then we also want, so that's the magnitude, but we also want to find the direction. And so to find the direction, we just want to find, we're just going to take the vector grad f at 1, 1, and we're going to divide it by the magnitude at 1, 1. So that was minus 4i plus 6j, and we found that the magnitude was 2 root 13. So I can simplify that. I'll take the 1 on root 13 out the front, and minus 4 on 2 is 2, and 6 on 2 is 3. Sorry, there's a minus there. So this vector that I've found here, so it points normal to the contour passing through A, in the direction of the contour f equals f equals 3. So it's normal to this contour here in the direction of this contour here, because that's the way, you know, our contours are increasing in this direction, increasing in this direction. So I guess it would be pointing in that direction there. Did anyone have any questions about question 3? No? Oh. Yeah, where would you like me to scroll down to? Maybe I'll zoom out if you can still. Is there? Is that the question you wanted to see? Yeah, cool. Okay, I'll move on to question. Which part of question 3 did you want to see? just the last part or a previous part? Part 3 of question 3. This one? No worries. Okay. So, we've got a function of x and y again, and I'm going to use so just to point x naught, y naught, we're going to determine a tangent plane approximation. So the first step we need to do is find the first order partial derivatives. So df dx is equal to 2x plus the square root of y, and the first partial derivative with respect to y is equal to x on 2 root y. So if we evaluate that at the point x naught, y naught, we have the function is equal to x naught squared plus x naught times the square root of y naught, and the partial derivative with respect to x at the point x naught, y naught is just 2x naught plus the square root of y naught, and with respect to y at this point, it's x naught onto y naught. And so now we have all the, all that we need to substitute that into the formula for this tangent plane equation. So the tangent plane equation is, so we'll call it T for tangent, Txy is equal to, so the function at x naught, y naught, plus the first partial derivative with respect to x at x naught, y naught, multiplied by x minus x naught, and then the same again except with respect to y. So y minus y naught. And if we substitute, up here what we found, we just get, so it's x naught squared plus x naught root y naught plus 2x naught plus root y naught x minus x naught plus x naught on 2 y naught y minus y naught. So now we have, I guess, a formula that. So if the surface was like this at any point x naught y naught, we would have sort of a plane at that. So instead of a function and having just a single tangent of a line, now we're sort of looking at it as a plane. So the next part of the question, we're going to use that tangent plane to approximate f at 1.73 with x naught y naught is equal to 1, 1. And I guess we've sort of chosen this 1, 1 because we know that the square root of 1 is 1. And it's also easy to square 1. So, we can easily find that without a calculator. So xy is equal to 1.73. And x naught y naught is equal to 1, 1. So using that tangent plane approximation that we had, so it was x naught squared, so that's 1 squared plus the square root of 1 plus, and it was 2x naught, so it was 2 plus the square root of y naught, which is 1, and that was x minus x naught, so x in this case is 1.7 minus x naught, which is 1, and that was plus x naught over 2 times the square root of y naught, which is 1, and then it was y minus y naught, so y in this case is 3 minus 1. So I think 2 plus 3 by 0.7 plus half 2, and I get 5.1. So, I can do that in my head quite easily without getting a calculator to find the square root of 3, or trying to square 1.7. So we've approximated it using the 0.11, but perhaps a different approximation may be better. And so we're going to do the same thing, except this time we're going to use the 0.24. So I haven't used an approximation because, so the tangent plane is the approximation, but the tangent plane at the point 1.73 is actually equal to 5.1, but it just doesn't, it's not on the function f. Yeah, cool. So we'll do the same again. So this time so we let x, y, so it's still equal to the 1.73, but this time the x naught, y naught is equal to 2, 4. And again, I know that the square root of 4 is 2. So, that's that. I guess that's why I've chosen to approximate using this this point. So this time we use the x naught, y naught as 2 and 4. So we just sub that into our tangent plane approximation. And this time, I'm not going to go step by step, but you can, I know 2 squared is 4, and I can add and subtract, so I get 5.7 because we're running out of time. So before we got 5.1, and this time we got 5.7. But I mean, I could use a calculator, and I see that and so I can compare these approximations to the exact value of 1.73. Value of the function at 1.7, x equals 1.7 and y equals 3. So if I use a calculator and sub those numbers into my function, I get 5.83449. And so I'm just going to swap to typing. So the approximation at 2,4 was a lot better than the approximation at 1. And it's in a better neighborhood than the other one, and we just get a better approximation. Does anyone have any questions about that question there? Cool. I'm going to move on because I'd like to get this last question done. So if we consider the function, so k is a function of f and x, and k is equal to f on x, and so we want to determine the approximate total differential at k naught. And so to do that, we'll need to have partially differentiate k with respect to f at the point f naught, x naught. And also the same, but with respect to x. The change. in X. So if we differentiate with respect to F first, we just get, so we're just keeping X constant, we just get 1 on X. So, if we evaluate that at F naught, X naught, we just get 1 on X naught. And if we do the same for X, so you might want to do that as F by X to the minus 1. So it's minus F over X squared. So at the point F naught, X naught, that will be minus F naught over X naught squared. And so now we've got the total differential is equal to this. And so the next question, so I've pointed out that this is Hooke's law, which you may be familiar with. It's the relationship between if you pull a spring with a force, the force needed to pull a spring a distance of x, that will so this formula. Sorry, the formula. The spring has a characteristic k that's always constant. So if you so perhaps say that we're doing an experiment and we want to find this k of the constant characteristic of the spring, and so say that the maximum relative error in the length measurement is taken to be 5%, and the maximum relative error in the force measurement is taken to be 1%. What is the maximum relative error in the computation of k? And so essentially we're looking for this here. So zoom out a bit. So the K naught we had is equal to F naught, X naught, and we had the total differential was this. And so I'm going to times this first term by F naught on F naught, so that we get F naught on X naught, changing F over F naught. And then I'm going to just split out this X naught squared term. So we get F naught over X naught, and then we'll put the other X naught here. And so we can recognize this F naught X naught as the K naught. And then if we divide everything through by K0, we get that we get this here. And so the question said that we had the maximum relative error in the force measurement, I think I said was plus or minus 1%, and in the length measurement, I think I said it was plus or minus 5%. So then we can find the maximum relative error in K will be given by, so 1% is 0.01 minus 0.05. And so I've sort of taken plus 1% and minus 5% for the length measurement, because that's going to give me the maximum error. So if I did 0.01 minus 0.05, I'm going to get 4%, but I can actually get an error of 6%. So plus or minus 6% would be the maximum relative error in K. Did anyone have any questions at all before?
Could I just review the question 5, the first part of question 5?
Yep.
Yeah, I got something not finished. Yep, thanks.
No worries. No worries. See you next time. Question 4. There was no question for 5. Was there? I can show you part 4. No problem. This one?